Hello friends, I am Snehal and we are studying differential equations. And today we will see another form of differential equations called exact differential equations. So let us start. Now before moving to exact differential equations, let us recall what does it mean by differential of a function. So suppose f is function of x. So we know that the derivative of f with respect to x is given by this formula, limit delta x tends to 0. So this is change in x, delta f over delta x. This is formula for derivatives. Suppose we plot this graph between f and x. So suppose it looks like this. Then if we take this point, let's call it x. So derivative of f with respect to x at this point means slope of this tangent line at this point. So if this angle is theta, we know that df by dx at this value of x is given by tan of theta. Okay. Now let's consider a small change in x. So let's take some other point. Let's say this point. Let's say this point. So this is the change is delta x. This point is x plus delta x. And if we find the corresponding change in f, so it will be like this. The value of f when x is this much, let's say f1. And when x is x plus delta x, the value of f is this much. So this is f1 plus delta f. So this is actual change in f. And we can find it approximately by using this formula. I can write delta f equals to, if I just take delta x on other side, I can write delta f equals to df by dx multiplied by delta x. Okay, and so this is tan of theta multiplied by delta x, and this much is, let's say, delta f prime. This is delta f. So tan theta is delta f prime, the opposite side divided by this adjacent side. So delta f prime divided by delta x. So delta x and delta x is cancelled. So we have delta f equals to delta f prime. So which is not quite true in this case. But if the change in x is small enough, this approximation becomes better and better. Okay, and in this small limit delta x tends to 0, this approximation becomes almost accurate, and then we say the change in f as differential of f, and we write it as df, not to be confused with this df. So it is df or dx, but here we are taking derivative and then multiplying it by this dx. Okay, so this is differential of f, and this one is differential of x. Now this is for the case of function of one variable. Now suppose we have a function of two variables. Now u is function of x and y. It's the function of two variables. Now how do we find the differential of u? Well, we find it in similar way as that of this. So du is differential of u, and it is just like this case, we need to take derivative of u with respect to x. But remember, there is this another variable, y is present. So we take derivative of u with respect to x, considering y as a constant, and this is called as partial derivative of u with respect to x. So this is partial derivative of u with respect to x multiplied by dx, just like this, plus since we have another variable, we take partial derivative of u with respect to y also and multiplied by dy. So this is complete differential of u. Okay. Now suppose we are given a differential equation in this form, m multiplied by dx plus n multiplied by dy equals to 0. So this differential equation is said to be exact differential equation if we can find a function u. So if there exists u, a function of x and y, such that this differential equation is complete differential of u. Okay, so this is exact differential equation if there exists u of xy such that differential equation is complete differential of u. So it means that m dx plus n dy equals to du. But we know that du equals to partial derivative of u with respect to x multiplied by dx plus partial derivative of u with respect to y multiplied by dy. So comparing this and this equation would be exact if and only if m equals to partial derivative of u with respect to x and n equals to partial derivative of u with respect to y. So equation is exact. This is exact if and only if m equals to del u by del x and n equals to del u by del y. Okay, but we don't know what is u. So how to check whether m equals to partial derivative of u with respect to x and n equals to partial derivative of u with respect to y? So this property of partial derivatives comes to our rescue. So it is, if you take partial derivative of u with respect to y and then you take partial derivative of that with respect to x, so it is equal to partial derivative of u with respect to x. So you take derivative with respect to x first and then take derivative of that with respect to y. Okay, so if we substitute m in place of this and n in place of this, what we get is del by del x of m, sorry, it is n equals to del by del y of m. So if this is true, the given equation is exact differential equation. So this is how we check whether given equation is exact or not. Now let us see, once we find whether given equation is exact, how to solve it. Okay, so suppose we have this differential equation m multiplied by dx plus n multiplied by dy equals to 0, and we find that this given differential equation is exact differential equation. So this is exact, and it means that m equals to the partial derivative of some u with respect to x, and n equals to partial derivative of u with respect to y, and therefore this differential equation equal to complete differential of that u which is function of x and y. Okay, so since du equals to 0, the solution of this equation is u of xy is constant. Okay, so this is the solution. So our job now is to find that u of xy which satisfies this differential equation. So let us consider that u of xy is equal to some v which is also a function of x and y plus f which is function of x only plus g which is function of y only. Okay, so let's consider this general form for u. Now m equals to derivative of u with respect to x, so m should be equal to derivative of v, partial derivative of v with respect to x plus derivative of f, and its function of x only, so its partial derivative with respect to x or derivative with respect to x, it is going to be same, so df by dx plus derivative of this g, but g is function of y, and that's why its derivative with respect to x is going to be 0. Okay, so we have del u by del x which is m, and it is equal to this. Okay, similarly let us find n. So n is going to be derivative of this u with respect to y, the partial derivative. So on right hand side we have partial derivative of v with respect to y plus, now derivative of function of x with respect to y would be 0. So we are left with derivative of g with respect to y. Okay, so now u is unknown, we need to find u, and we have m and n as given. Okay, so now let's try to integrate m and let's try to find what do we get. So integration of m dx. So from this we get integration of m dx as integral of dv by dx del v by del x times dx plus integral of this term. So it is df by dx multiplied by dx. And since the integral is antiderivative, we get integral of this term should be v, because we are taking derivative with respect to x and then we are integrating using x as an argument. So we have v, which is function of x and y, plus f, which is function of x only. So if we integrate from this given equation m only, so from required u, what we get is this part of u. Okay. And similarly, if we integrate n, so let's do that. Integral of n dy is integral of this term plus this term. So we have integral of del v by del y times dy plus integral of the second term dg by dy times dy, and which is equal to, again, since integral is antiderivative, we have v of xy plus from here we have g of y. So if we integrate n, we get this. So you can see that this term v of xy is common in both the integrals, and for u we need v of xy plus f plus g. That means if we take the integral of m dx, what we should take from integral of n dy is this thing only. So what does that mean for us? U is equal to integral of m dx, which will give us this part of u, plus it is something from integral of n dy, and that something is terms in n not containing x times dy. Since v is function of x and y, this term del v by del y, it may contain x, but this term del g by del y, sorry, dg by dy, it won't contain x. So this is the solution. Okay. So since we wanted g only, we'll take terms in n not containing x and integral of that. So this way we'll find the solution to this exact differential equation. And remember, the solution is this u found this way, it is constant. Okay. So now let us see some problems on exact differential equations. So let us see problem number 1, and it is x square minus ay multiplied by dx plus y square minus ax multiplied by dy equals to 0. Now let us check whether this given differential equation is exact or not. And for that, we need to compare it with m dx plus n dy equals to 0. And comparing, we get m equals to x square minus ay and n is equal to y square minus ax. Then we need to find partial derivative of m with respect to y and partial derivative of n with respect to x, and we know if these partial derivatives turn out to be equal, our given differential equation would be exact. Okay, so Because we are taking partial derivative with respect to y here, this x is a constant, x square is constant. That's why derivative of this term is 0 and derivative of second term is just minus a. Similarly, here we are taking partial derivative with respect to x. So derivative of y square with respect to x is 0 and derivative of second term with respect to x is just minus a. And they are equal. So we have partial derivative of m with respect to y equals to partial derivative of n with respect to x, which means that the given differential equation is exact. Okay, then we know how to find solution of this given differential equation or exact differential equation. So solution is, since this can be written as du and we have du equals to, this term is du equals to 0. So solution is u of xy equals to constant, and we find that u of xy as m dx, integral of m dx plus integral of terms in n not containing x, so not containing x, so integral of that with respect to dy. So this thing is u and solution is that u is a constant. So this thing is constant. Okay, so let's find that solution. So we have m equals to x square minus ay. So integral of x square minus ay dx plus, there are two terms in n, y square and minus ax, and we want terms in n which do not contain x. So there is only one such term, which is y square. So here we will have y square dy, and this is a constant. Integral of x square is just x cube over 3 minus, here we can take ay outside, it is a constant, and we have integral of dx only, so which is x plus, multiplied by this ay plus integral of y square, which is y cube over 3, and this is constant. So this is the solution of this given differential equation. Now let's see another problem. Now let us see problem number 2, and it is sin 3x plus sec y square dy by dx plus 3y multiplied by cosine of 3x equals to 0. Now we need to check whether this given differential equation is exact or not, and if it is exact, we will solve it by the method we just saw. So for that, let us rewrite this, since there is this dx here, dy by dx. So I will multiply whole equation by dx, differential of x. So I get sin 3x plus sec square y dy plus 3y into cosine of 3x multiplied by dx equals to 0. Then we'll compare it with m dx plus n dy equals to 0. We get m equals to 3y into cosine of 3x, and n, we get sine 3x plus sec square y. Okay, now in order to check whether this is exact or not, we need to find partial derivative of m with respect to y and partial derivative of n with respect to x. If they happen to be equal, the differential equation is exact. Okay, so here we'll find partial derivative with respect to y. So this cosine 3x for this case is constant, and therefore derivative is just 3 into cosine 3x. Okay, and here terms containing y will consider to be constant, and we have only one term containing x, which is sine 3x. So derivative of that is cosine 3x multiplied by 3. So we have partial derivative of m with respect to y equal to partial derivative of n with respect to x, and therefore we know that the given differential equation is exact. Therefore given equation is exact. Now we know how to solve this. So the solution is integral of m dx plus integral of terms in n not containing x dy, and that is equal to constant. Okay, then this is m and this is n. So integral of m dx is integral of this term, which is 3y cosine 3x dx, plus integral of terms in n not containing x. So we have, this is n, and terms in n which do not contain x, there is only this term, which is sec square y dy, and it is equal to constant. Now here we are integrating with respect to x, so x is argument, 3y we can take outside safely, and integral of cosine of 3x dx, we have integral of this is just tan of y. This integral is sine of 3x divided by 3, and we have the 3y in multiple, so this 3 and 3 they get cancelled out, plus tan of y equals to c. So solution is y multiplied by sine 3x plus tan of y equals to constant. Okay, so now we know how to check whether given differential equation is exact or not, and method to solve exact differential equations. With this we finished all the major forms of first order differential equations. From next time we'll see applications of first order differential equations. Thanks for watching.